In 1834, Hamilton published the principle of least action, or sometimes called the principle of stationary action. This can lead to the theory of everything. It opens up the world to a whole new gamut of information that wasn't there during the Newton classical mechanics world. So, what I want you to do is take a look at the next few screens on this video and read carefully what's there, and then I'll come back and make some comments. Are you still with me? I hope so. The idea that Hamilton's principle actually led to a version of classical mechanics that not classical mechanics that allowed us to view quantum mechanics, and also that it was based on the work of Lagrange, another video that I had. So think about these things as we go forward and as I try to put the math in a perspective that's not too highbrow, too complicated to get through on your first view. Upper left hand corner. This should be review from my video about Lagrange and the Lagrangian. This is the Lagrangian. It shows kinetic energy. That's the standard there. Notice the x with the dot above it. That's the same as the first derivative of x with respect to time, which is velocity. So 1/2 mv squared minus mgh. That happens to be our potential energy for a falling object, as with g being that you're on Earth for the gravitational acceleration. Now, here we're going to go through a couple other things. This is the Hamiltonian extended. The Hamiltonian extended says that the P, which is momentum, normally we call that just simply m times v, P momentum times velocity, this is x dot, which is velocity, minus the Lagrangian. Notice I've got that little tilde above the h. That means it's extended. What we want to do is find the simple Hamiltonian. Now let me spread this out. This equals P times x dot, and then I'm going to take the Lagrangian, which is over here, minus 1/2 x dot squared plus mgx. Now, can we substitute m for p? Yes, we can. We can do that. That is p equals the partial derivative of the Lagrangian with respect to x dot. Now, using the exponent rule, the 2 times the 1/2 gives me 1, so that gives me m times x dot minus 0. The partial with respect to x dot over here is 0. So, doesn't that look familiar? M times v. So, what I'm going to do is plug in for momentum m times v, or m times x dot. That gives me m times x dot squared minus 1/2 m times x dot squared gives me 1/2
1 times 1 half minus 1 half gives me 1 half, 1 half mx dot squared plus mgx. And that is the kinetic energy plus the potential energy. So the Hamiltonian gives me a, a sum of kinetic and uh, potential energy. So how do we work with that? What's new about that? That's the total energy, But the least action gives me the Hamiltonian gives me the energies at the the energy at the maximum of these things. So we maximize these things, gives us the principle of least action or stationary action. Now, here's a definition. The simple Hamiltonian, which is a function of momentum. Notice up here we got momentum and velocity, or x dot. The definition, that's what the three uh, dashes here are for, not equals, but defined as the maximum of the velocity. The maximum of velocity where we have the extended Hamiltonian, which is a function of momentum and the velocity. Momentum and velocity, notice we can hold the uh, momentum constant and come up with a maximum velocity for these two things. Now, that gives us the extended Hamiltonian as a function of momentum and a function. Momentum, which is a variable, independent variable, and x dot, which is a function of the momentum itself. So notice this is a functional, this is a variable. This is a little bit different for things. It's not just a simple maximum. So here we have h, which is a function of momentum, h momentum, and also x. That's not x dot, that's just x. So this is here what Hamilton wanted to do, is put all this stuff in terms of momentum and x. And here's the momentum in terms of the kinetic energy and potential energy. P squared over 2m. So here's the difference here. You think, well, P squared over 2m, that's the same as 1 half mv squared, which is just what we knew anyway. But this is P squared over 2m at the maximum velocity. At the maximum velocity, this gives us the principle of least action, which is what we're trying to get to. Principle of least action, principle of stationary action.
All right, let's absorb what I just said. The Hamiltonian is kinetic energy, potential energy added together at the maximum velocity where momentum's held constant. That's what we're talking about, and that's why the Hamiltonian is so important. It gives us that specific energy where nature is going to go. And when we look at the uh, quantum mechanical world, we'll have a Hamiltonian operator which will operate on a system of some kind of coordinates. It could be an infinite dimensional space, which, if you look at my In Search of a Quark, we've got that infinite dimensional space. So, as you look at this stuff, think about that and hold on to that. If you forget what the Hamiltonian is, do two things. Watch the Lagrangian video and then watch the Hamiltonian video. And then you can go in search of a quark to find some of these things and figure out what to do.